Hello everyone, welcome to this video on copula. In this video, we introduce the copula method, which provides a flexible way to introduce or model the dependence between random variables separately from their marginal distributions. We shall examine its theoretical foundations, including Sklar's theorem, and illustrate how copulas can be used to construct joint distributions and generate dependent data. Uh, we will start the discussion with the most important theorem related to this, that is Sklar's theorem and also its converse. So Sklar's theorem tells that if uh, tells that a joint cumulative distribution function can be represented through something called a copula, so that the joint distribution can be written as a function of its marginal CDFs. Right. So the theorem says let capital F x comma y, that is the notation for the joint cumulative CDF, be the bivariate joint CDF with marginal CDFs Fx and Fy. Then there exists a copula C such that the joint density, joint CDF is equal to a function of individual marginal CDFs. That function is denoted by C and it's called a copula. Right. So the main idea is that the joint CDF can be written as a function of individual marginal CDFs. So Sklar's theorem says that there exists a function C, so that we can write down the joint CDF in this way. And in particular, if Fx and Fy are continuous, this function C is unique. Otherwise, C is uniquely determined on the range of Fx and range of Fy, that the product of those two intervals. Right. So what we are considering in this video is only continuous cases. So we are considering X and Y to be continuous random variables having continuous joint CDF and continuous marginal CDFs. So that is what Sklar's theorem says. Right? There exists some function C called copula that separates the joint distribution into a function of individual marginal CDFs. And conversely, let C be a copula. Let's C be some function like that, and let Fx and Fy be any univariate CDFs. Then if you substitute those Fx and Fy into the C, you get some function. And that function gives us the joint distribution of X and Y. Right. So that's the converse of the Sklar's theorem. Conversely, let C be a copula and let Fx and Fy be any univariate CDFs. Then if you consider C of Fx, Fy, and let's call it this notation here, Fxy, Xy, and with the superscript C to denote that is a function created through the C, And this function is a CDF, joint CDF. So bivariate joint CDF with the marginals fx and fy. Right. So now we will look at, first of all, we'll find out what this unique C look like. What is the form of this unique C if x and y are continuous, and if fx and fy are continuous CDFs. And then we will show the converse, that when we apply this fx and fy into any copula, you will get a joint density function of x and y with marginals. Marginal CDFs are actual marginal CDFs of x and y. Right. This Sklar's theorem is, and its converse actually is nowadays considered a very important theorem, and it has a lot of uses. So what are those importances? Sklar's theorem separates the joint distribution into its marginal distributions and its dependent structure represented by a copula. Right. So this function C separates the joint CDF into a function of marginals, and also inside that function, C captures the dependence between x and y. When the marginal CDFs are continuous, the unique copula completely describes the dependence between the random variables. Right. So the copula contains somehow or captures the dependence between x and y. The converse allows any copula to be combined with any chosen marginal CDFs to construct a valid joint CDF. So this converse is useful when, say, for example, we want to generate some data from a joint distribution with marginals, given marginals, marginal CDFs or marginal densities, where the joint distribution may not be exactly known, but the marginals are known, and also the dependent structure between x and y is also known. In that kind of situations, we can use any copula. Actually, not any copula. We have to choose a suitable copula. Choosing a suitable copula and inserting the required fx and fy into the copula, we can get a function like this, and that will be a joint cumulative distribution function of x and y. That will be a joint CDF. It may not be exactly equal to the actual joint CDF of x and y that we consider, but anyway, this will also be a certain joint CDF. And the important thing is that that joint CDF will give us the actual fx and fy as its margins. And also, if this copula that we choose contains the covariance structure that we want between x and y, then this joint distribution will be a suitable joint distribution to describe the actual joint CDF between x and y. And using that, we can generate data. We will discuss how to do that in this video. Thus, the marginal distributions and dependent structure can be selected and modeled separately. Right? Choosing a suitable copula that captures the covariance structure in our problem, then we can use this converse of the Sklar's theorem to get a joint distribution, and from that joint distribution, then we can generate the data. Right. So as I mentioned, now we will look at what is the form of the unique copula when x and y are continuous. So let xy have joint CDF fxy and the continuous marginal CDFs denoted by capital Fx and capital Fy. Let Cxy, instead of just C, I am calling it Cxy here because later on I am going to consider the copula for two other variables also. Therefore, to distinguish those two, I will use two different notations rather than using C for everything. So let Cxy be the unique copula supplied by this class theorem related to the joint distribution of x and y. And let u be, capital U be, fx evaluated at capital X. So this is a random variable. It's denoted by u. And v, fy, y. We already know, then if you define u to be like this and v to be like this, the CDF evaluated at the random variable, those are also random variables. And u has a uniform distribution in 0, 1. V has a uniform distribution in 0, 1. Then we can show that this unique copula given by this class theorem is having this form here. So Cxyuv will be actually the joint cumulative distribution function of this u and this v, evaluated at this simple u and simple v. And also we can show that with more details, we can show that it has this particular form, that is, we can get that expression in terms of fxy evaluated at fx inverse u and fy inverse v. Now there's an important thing to understand here. These u and v are not just independent uniform random variables, because u here in particular is defined as fxx and v is defined as fyy. So if x and y are dependent, there is some dependent structure, then that dependent structure will be coming into the dependence between u and v as well. It will not be the same dependence, but there will be, these will also be dependent in that case anyway. U and v will be dependent. But on the other hand, the simple u and simple v are any two real numbers between 0 and 1. Right. So that is an important thing to understand. So here we talk about this u and v, and these will be here. Therefore, this fuv is actually the joint distribution of this u and this v, evaluated at any simple uv point. Right. So let's prove this theorem. Right. That means we will show that that unique function or the unique copula related to the joint cumulative distribution function fxy is given by this form here. And then for a particular fxy, then we can get the actual expression. But generally, this is the form. Right. So in order to prove this, we consider u and v as we mentioned earlier here, u to be fxx and v to be y. And from our theory that we have learned before, we know that u is uniform in 0, 1, v is uniform in 0, 1. That means both are standard uniform random variables. Now let us consider the joint cumulative distribution function fuv and denote the joint CDF denoted by this thing. And then for any uv in this interval 0, 1, just define fx inverse u to be xu and fy inverse v to be yv. And this fx inverse and fy inverse exists because fx and fy are continuous functions. Since fx and fy are continuous, from this definition, we can also get u as fx evaluated at xu and v as fy evaluated at yv. Right. Now, let's look at the cumulative distribution function, CDF of u and v. So this is the joint CDF. By definition, that is equal to probability u less than or equal to simple u and v less than or equal to simple v. Remember, these u and v are not independent independent uniforms. They are dependent because they came specially from this definition here where x and y are dependent. So this one is, we can write down, this is u is equal to fxx, therefore replacing u by fxx and v by fyy, you can write down like this. And then you can write down, this is the same as x less than or equal to fx inverse u, which is xu, and y less than or equal to fy inverse v, which is yv. So now this is actually the same as the joint cumulative distribution function of x and y evaluated at the point xu, y. Right. So this one. So in one way, we have proved that the joint CDF of u and v evaluated at the simple u, simple v is equal to this expression. On the other hand, by the class representation, fxy, right, class theorem, it says there is a unique copula, and that copula cxy is given by this definition here. So therefore, fxy xu yu should be equal to cxy uv also, right? Because this is simple u and simple v, right? So now we have two expressions, right? Fxy xu yu is equal to this expression, and also fxy xu is equal to this expression. So therefore, those two gives us cxy uv is equal to fuv evaluated at uv, right? So therefore, it says cxy uv is equal to the joint CDF of uv. So that is one form of this unique copula related to the joint CDF of x and y. Thus, the copula cxy is precisely the joint CDF of the probability integral transform, right? Because these are called probability integral transforms, right? These functions, right? So because u is equal to fx inverse, this came from this expression here. So cxy uv is equal to fuv uv, but fuv uv is equal to fxy evaluated at xu and yu. Therefore, that is fxy. Xu is fx inverse u, and yu is equal to f inverse v. So that is another expression that we can use for this unique copula. Right. So one way to express that as the joint CDF of u and v, where u and v are directly coming from related to x and y. Or it can be expressed in this way. So we will use that representation, mainly this representation later on, to get an expression for a particular for the copula related to a particular CDF when it is given to a particular joint CDF. Right. So here again, it emphasizes what I have already mentioned. The random variables u and v are the particular uniform random variables obtained by applying the marginal CDFs to x and y. Right. So that means u is equal to f of x evaluated at capital X, and v is equal to f of y evaluated at y. So in contrast, the simple u and v that we considered all over here are just two numerical numbers in 0 and 1 interval. Although u and v are individually uniformly distributed, they are not generally independent. Their dependence is inherited from the dependence between x and y specified by fxy. Right. So this bullet item should have gone here and then this later. Right. So these two are going together, the first one and the last one. Right. So now let us look at an example and let us derive the copula, the expression for the copula. And we will see that the joint distribution that we consider can be written as a function of individual CDFs, marginal CDFs, through this copula, using the copula. Right. So here, these things are mathematically intensive, and therefore I'm not going to explain every line here. I'm just showing the example and giving you the idea. So let's consider a pair of random variables x and y, and suppose it has this particular joint density function. Joint CDF, joint cumulative distribution function, this capital F. Right. Then we can obtain the marginal CDFs for x and y by just letting y go to infinity. We can get the marginal CDF of x, and that is given by this expression, right? Because we need to identify the marginals to see that the copula actually separates the joint CDF into a function of CDF, copula gives us the joint CDF as a function of individual CDFs. So in order to see that, we have to know individual CDFs also, marginal CDFs. So fxx is given by this expression, and similarly by letting x go to infinity, we can get the marginal CDF of y, and it has this expression. Right. And also there are inverse functions, so the quantiles are given by these expressions. Once you know this function and this function, we can get the inverse function by setting, for example, u equal to fxx and solving for x gives us this expression, the inverse of fx. And similarly, by letting v equal to fyy and solving for y, we get the inverse of fy function. Those are given by these expressions. So according to the theorem that we just mentioned, we know that the unique copula should be in this form, right? So therefore, we now know the joint CDF. We also know the inverse functions. So therefore, if we substitute those functions into this copula function, we get this expression here, right? So C evaluated at uv is given by this expression. So fxy, we know it is equal to this expression, right? This related is written as a function of x and y. But what I want here is a function of fx inverse u and fy inverse u. So wherever I have here x, I have to write down fx inverse u, which is equal to this expression. And wherever I have y here, I have to write down fy inverse v, which is equal to this expression. So when I substitute those terms, I get this expression for the copula. Actually, I could have used this, or named it this by c x comma y, but in this case, we are looking at only one copula. Therefore, it's okay to just mention it as c. So this is the function for the copula, right? Now, for example, u is fxx, f subscript x within bracket simple x, v is f y simple y. So therefore, and we know that according to Sklar's theorem, the joint CDF should be equal to this copula, right? So therefore, if I substitute u and v by fxx and fyy, I get this expression, right? So therefore, the joint density, which is equal to the copula according to Sklar's theorem, and this is equal to this expression. And when you substitute fx x for u and fyy for v, you get this expression, right? So from this expression, it is very clear that this original joint CDF, which was a very complicated expression, and here it is not clear how this can be written as in terms of the individual CDFs. But now it is very clear to us how the same function can be written in terms of individual fxx and fyy. Right. So here everything is in terms of fxx, fyy. Right. So that shows actually what this class theorem says. Right. Through the copula, we can separate the joint CDF into a function of individual marginal CDFs. Thus, the joint CDF has been represented in terms of the marginal CDFs fx and fy, and the copula function itself has been found. The marginal CDFs describe the distributions of x and y separately, while the copula C determines how x and y are dependent. So the dependent structure of x and y is included in this expression. For example, in this copula here, the same copula, you can see that's a function of u and v, and in addition to that, there's a parameter, right? So therefore, we can consider this as a function with some parameter. And if you, for example, look at, say, theta is equal to 0, then CUV, which is the same as the joint CDF, is equal to u and v. And that shows that when theta is equal to 0, u and v are independent. Right? So the independence or dependent structure, that's how we say it's included in this thing. And similarly, if theta takes some other value, there will be some covariance coming out of this between u and v, random variable capital U and capital V, I mean. Right? Because CUV, as we showed, is actually the CDF of joint CDF of U and V. Right. So this expression describes the dependence between x and y through theta. Theta equal to 0 represents the independence between u and v, while positive and negative values of theta represent positive and negative dependence respectively. So you can understand that if you put a positive value here and use this joint CDF to find out the covariance between u and v, you will see that it's a positive value. I have not done that part, and we can identify that. So therefore, you can see that in this copula, the dependence is described through this theta. Dependence between u and v is described through the theta. Right. Let us look at another example. In this case, we are going to look at a very famous copula called Gaussian copula. And we will be using the Gaussian copula later on to generate data also. So in this case, we are considering the copula related to the joint bivariate standard normal distribution. Right? That's what you mean by the Gaussian copula. In other words, we should be able to write down, according to this class theorem, we should be able to write down the joint CDF of Z1 and Z2, where Z1 and Z2 are individually having standard normal distributions, we should be able to write down their joint CDF using a copula, right? And that copula is called the Gaussian copula. Right. So let Z1, Z2 have bivariate standard normal distribution with correlation coefficient rho. Right. So in this case also there is going to be a parameter. In this case the parameter is rho, where rho is going to be between -1 and +1. Right. So here we are going to use some special notations rather than a capital F always, because when you talk about standard normal, there is a special notation. For example, the density function of a standard normal distribution is usually denoted by simple pi function, right? Simple pi, right? So, for example, f z is in particular denoted by pi z, right? So, we will be using this notation. This is simple pi. Sorry, this is capital pi. F z, capital. Right. On the other hand, the density function f z is usually denoted by simple pi z. Right? So we'll be using this notation also here. Right? And also the joint uh, CDF, f z1, z2 evaluated at some value z1, z2 will be denoted by, in this case, capital pi rho, right? So that to distinguish this one from this one, we are writing pi rho actually. Here there is no rho. This is only for one z, for example, z1, z2, and so on. But here, for the both random variable, we are looking at the joint CDF. So there is a row involved. Therefore, we use that row to distinguish the CDF from this pi here, right? Okay. So that is the notation, right? So this you could have denoted actually this one by pi 1 and right. So here let me go through this again. Let Z1 Z2 have bivariate standard normal distribution with correlation coefficient rho. Denote is joint CDF, which is in the usual notation, this one, but we will specifically use this notation, capital pi rho within bracket Z1, Z2 to denote this. And both marginal distributions are standard normal. So therefore, it's enough to use the same notation pi, because this this marginal distributions means marginal CDFs here, right? So F, capital F, is capital pi, capital pi. If we want, we can denote this by pi 1 and pi 2, but pi 1, pi 2 both will be pi. And we will also use pi inverse to denote the inverse of this function, right? So by Sklar's theorem, directly we can get the expression. So in this case, instead of writing down C Z1 Z2, we write down for short notation C rho here. That's indicating the copula related to Z1 Z2. Right. So that's the same as if we write down, use the previous notation. This will be the same as C Z1 Z2 U. Right? That's what I denote by C rho here. And that's according to this formula that we got earlier. We can substitute the expression. So this expression is pi rho. This is just pi rho. And this one is pi inverse U. This is pi inverse. This is pi inverse U. Right? So this copula given by this expression is called the Gaussian copula. Right? Gaussian copula. In order to see how FZ1 Z2 is written as functions of fz1, fz2 separately, we can expand that, right? So this C rho is given by like this, uh, because U and V now we can replace, because U is equal to pi z1 and V is equal to pi z2. That is, this is capital F z1 evaluated, that is z1. This capital F z2 evaluated, that is z2. So using this notation, I can write down this expression, 0 uv, as this. And then this part, this u and this v can be replaced with phi z1 and phi z2, right? So here, actually, this one is f is z1, this f is z2, and this f is z1 and f is z2. So if I write down in terms of the earlier original notation, I can write down this, because we know that from this class theorem, this unique copula should be equal to the joint CDF. So therefore, the joint CDF of Z1, Z2 is equal to this copula. But now I am replacing phi Z1 as F Z1, Z1 and F Z2, Z2. Then we can see this is the final version that we can show actually. So it's clear that this expression shows the joint CDF as as a function of individual CDFs, individual marginal CDFs through this function. So this represents the joint CDF in terms of the marginal CDFs FZ1 and FZ2 and the Gaussian copula 0 here. The marginal CDFs describe the individual distributions of Z1 and Z2, while C rho describes the dependence between Z1 and Z2 through the correlation parameter rho. For example, when rho is equal to 0, if I go back to the simple formula, when rho is equal to 0, this thing which is equal to the joint CDF is equal to we can show that it is equal to U times V. Right. When you substitute this into the expression with rho equal to 0, you will see that this function is equal to U times V. It's not directly visible from this expression because the joint density is a very complicated function. But if you really substitute rho equal to 0, in that case, you will see that this copula gives you this expression. So that shows you that when rho is equal to 0, the random variables u and v are uncorrelated. And from previous lecture, we know that for a joint bivariate normal distribution, when two random variables are independent, the two random variables are uncorrelated. That means when rho is equal to 0, then they are independent as well. Right. So if rho takes some other value, then that will be inside this function. If you actually calculate, you have to give a value for rho, and that's how the copula captures the dependence between Z1 and Z2 through that parameter rho. Right. So that is the first part. So in that part, I just explained the class theorem, direct theorem, and the converse of that. The direct theorem gives us the expression for the copula, right? The unique copula, especially when when the marginal CDFs are continuous. And the converse, on the other hand, shows if you substitute fxx and fyy for u and v in any copula, then we get an expression, and that expression actually gives us a CDF, joint CDF between the two random variables, right? So later on, we will use that CDF to generate data, right? So that the important thing will be selecting a suitable copula which captures or which we will be able to approximately capture the actual dependence between the original variables through that copula. Right. Now, here I'm going to prove the converse actually. Right. So I have not proved the converse of this class theorem yet. So here I'm going to look at it. So suppose the actual joint CDF of XY is unknown. Right. So this is important when in that kind of situation. But suppose the desired continuous marginal CDFs Fx and Fy are known and some information about the dependence between X and Y is also known. Right. So consider that situation. So because when we don't know the joint CDF, we need some CDF capturing the dependence as well as from that CDF, we should be able to get individual actual marginals as well. Right. So a suitable parametric copula family can be selected and then used to construct the joint CDF and generate data. A dependence measure such as the target correlation does not by itself uniquely determine the copula family, right? Sometimes some other parameters may also be important, required depending on the family that you are using. Right. Suppose now here we are going to look at some copula like well-known copula, like for example, Gaussian copula. So in general, I'd say I will consider a copula related to a non-copula related to two random variables P and Q. Right? Copula related to the joint CDF of two random variables P and Q. And let us denote that copula by C PQ. Right? And the unique copula for that uh, related to the joint CDF of PQ is given by this expression according to the Sklar's theorem. It will be FPQ evaluated at this quantity. Right. That's what we have already obtained in the previous part. So now we will use this copula, but instead of F inverse PU and FQ inverse V here, we will use here the inverse CDF of X and Y. So by converse of the parts, part of Sklar's theorem, the function, this function here, when you, right, so here C, P, Q, U and V. So if you substitute instead of U here is equal to FP P and V is equal to FQQ. Instead of those two, if we substitute Fxx and Fy, we get some expression and we denote that expression by this notation. We don't know yet what we are going to get. Right? If we substitute here, for example, F, capital F, U, this U is equal to some capital F, capital Fp evaluated at P, and this V is equal to Fq evaluated at Q, then what you get here is actually the real CDF of joint CDF of PQ. That's what you will get. But if you instead of F of P evaluated at some value P and F of Q evaluated at some Q, if you substitute Fx and Ffy, you get some expression still, but that expression will not be equal to the actual joint CDF of x and y. It will not be equal to the actual joint CDF of x and y. It will not be equal to the actual CDF of P and Q also. It will be some expression. For the moment, let us denote it by this notation here. Right. But what we are going to show is that this expression that we get by doing this is actually a CDF. That is one thing we are going to prove. And also we are going to prove that the marginals coming from this joint CDF, marginal CDFs are individually fx and fy. So two important things, right? So by using some known copula, we can have we can get some joint distribution for x and y. We don't know the actual joint distribution, joint CDF of x and y. But using this method, we can get some joint CDF. The importance of that is from that CDF, we can get for that joint CDF, the marginal CDFs are actually the actual marginal CDFs of x and y. So that is important. Right. So let's first show that this expression actually is a CDF, joint CDF. And then by letting the arguments one by one into infinity, we can find out the marginal CDFs. Right. So now let's consider this quantity. Right. For a copula, it's a well-known property. You can prove that. Right. Every copula, for any copula, right? See, if you put one argument to one, so in other words, if you put this function equal to infinity here, then you get u, see u1 is equal to u and c1v is equal to v. So this is a well-known result of any copula. So this result should be valid for our copula, this one also, because this is also a copula here, CPQ. Right. So therefore, let's calculate CPQ and let the second argument equal to 1. Therefore, the answer should be the first argument here, fxx. So that is coming from by putting infinity for the second value here. So therefore, this value is equal to fxx. And this value here, putting 1 equal to 1 in the copula is equivalent to putting infinity in this expression for the first argument. And according to this one, this is equal to fyy, right? So it means this is actually a joint CDF, right? Joint CDF are the functions which have this property. When you put one argument to infinity, you get the marginal of the other argument, right? So the marginals of the constructed function here are the actual marginals, right? So that is one thing we have proved. Actually, we have not proved that this is a CDF yet. In order to prove that, let's look at this part here. So let's take U to be FPP and V to be FQQ, where P and Q are generally related. And let's define X star to be Fx inverse U, right? So first get the U value using P and V value, V random variable V by using Q. And then transform those U and V into X star and Y star by considering inverse CDF of X and inverse CDF of Y. And let's consider these two. And then if you look at the joint CDF of X star and Y star at evaluated at some value XY, by definition, it is equal to this expression. And because X star is equal to this one, you can write down this expression as U less than or equal to this and V less than or equal to this. And this one is actually the copula, right? Because this is the copula of PQ evaluated at fxx and fyy according to the definition of the copula. This copula is defined using these two lines, right? When you take u to be this expression and v to be this expression, this copula is defined. This equal to this. So therefore, this equal to this. That is the definition of the copula. And but what we now see as this one is actually is what we have got this one here. Right? So therefore, that is equal to that. So therefore, actually, this expression earlier we didn't know what that was. Only thing we know is that when we put infinity for one argument, we get the marginal CDF of x, and when we put the first argument to infinity, then we get the marginal CDF of y. That's one thing we saw. But now we see that this is actually a CDF, joint CDF between this x star and this y star. So therefore, it is a CDF. It may not be equal to the actual CDF of original x and y, but this is the CDF of x star and y star, right? So it is a joint CDF. So now, because when you put that one argument to infinity, you get the marginal. So that marginal is equal to fxx. The other marginal is fyy, right? So that shows the converse of this class theorem, right? So according to this part here, we see that this expression here is actually a joint CDF. Its copula is CPQ, right? So these are joint CDF now. Its copula is CPQ. Right. So this is the theorem. This converse is the part that we usually use to generate data for random variables x and y with marginals, given marginals fxx and fyy, and given dependent structure. Right. So suppose copula C has been selected to model the desired dependence. Right. So remember, when you select the copula C, what is important is we should be able to capture the dependent structure in x and y using that copula. Right. So there are so many copulas uh, 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 defined by a lot of people, like uh, Gaussian copula, T copula, and some other copulas. The way that they capture the dependence between the two variables is different, right? So by examining the existing dependence structure between x and y, we may be able to select one of those well-known copulas to capture the dependence between x and y in our problem. Right? Then obviously using that copula, we can get the marginals of always the required marginals. The important thing is to capture the actual dependence as close as possible. Suppose a copula C has been selected to model the desired dependence. Assume that C is differentiable with respect to its first argument and the argument, and that the required conditional inverse can be obtained. Right. So in order to get the data, actually generate data, this is required. Right. So we will discuss that later, because otherwise it will not be clear if I explain it right now. Right. So what is required is, first of all, get this expression here, joint CDF, right, generated by some well-known copula. Right. And then we will be generating data as described here. Right. So I have written down some steps that generally used. Right. So generate two independent uniform random numbers, say u and w, from standard uniform distributions. They are independent. Generate them independently, U and W. Then, using the Copula formula, calculate the conditional CDF of V given U is equal to U. Right. So once we have this expression, right, the copula is equal to the conditional CDF. So from using this conditional CDF, sorry, this is the, sorry, not the conditional, this is the joint CDF. Using this joint CDF, we can get the conditional CDF of uh, uh, the second variable given the first variable. Right. So here, what we do is, using the copula formula, calculate the conditional CDF of V given U is equal to U. Right. So conditional, the copula CUV is actually the joint CDF between U and V. Right. From that, we can get the conditional CDF of V given U, and that we have to get some expression. Yes, I will show you an example later on. So that is the second thing. And then generate V by using this formula. So let this conditional V given U to be equal to the W that we generated here. And solve this equation, right? So U is now known, only V is unknown. So this is an expression in terms of U and V. So you substitute the value that you get for U, and W is now known value. Only thing unknown is V. So in other words, V will be equal to F inverse V given U evaluated at W given U. Right. So that is why it is important for us to be able to get the inverse of this function. Otherwise, we will not be able to get this V here. Right. If we can get this V in this method, in that case, this random variable corresponding to this U and the random variable corresponding to this V will be correlated. Even though U and W are independent, they are uncorrelated. When we generate V using this method, the original U and V will be now correlated. So once we have this U and V, we use now those U and V to get the correlated X star and Y star. Right? So let's define X star to be Fx inverse U, where Fx is the marginal of X that we want. Y star, let Y star be the Fy inverse of this V here. Right? So because this U and V are correlated, this X star and Y star will also be correlated. It will have some correlation. That correlation will be captured by the selected, will be included in the selected copula here. Right. So record X star Y star as once generated observation and repeat the same thing again and again to generate more pairs of X star Y star. Then those X star values can be considered as a random sample of observations from the marginal CDF of X. And similarly, Y star values are random numbers from marginal CDF of Y. But of course, the joint distribution of those X star and Y star values will not be exactly equal to the joint distribution, the actual joint distribution of X and Y, which is unknown to us. But by selecting a suitable copula to generate this U and X star and Y star in this method, we will be able to maintain the dependent structure, at least approximately, we will be able to maintain the dependent structure between X and Y in X star and Y star as well. So therefore, X stars will have the marginal, exactly the marginal that we want. Y star values will have exactly the same marginal as we want, but the joint distribution of X star and Y star will not be equal to the actual joint distribution of X and Y. But nevertheless, the dependence structure between X star and Y star will be approximately equal to the dependence structure between X and Y. Right. So by choosing a suitable copula, we will be also able to get the actual the CDF between X star and Y star to be as close as possible to the actual CDF between X and Y also. So that is the procedure that we'll have to use to generate data using copula. So in this particular case, we are using actually the converse of the Sklar's theorem. Right. So I have included some other theory here, but I am going to omit that part. What I have shown here is actually uh, that because in order to get this expression, we need to take the derivative of the copula, right? We are going to get this expression by taking the derivative of copula, and this expression uh, I have not proved, I have just mentioned here. And we can actually prove that this conditional CDF of V given U is actually equal to the first derivative of C with respect to the first argument here. That we can prove, and I have the proof here, but I'm going to omit it because it's going to take some time, right? Uh, and also, I have proved that this X star Y star, that's the joint distribution of X star and Y star, actually has the marginals. We have already proved it when you're proving the converse of the Sklar's theorem, actual marginals of X and Y, right? So, as a summary of this part, the selected copula determines how the generated variables, that is X star and Y star, depend on each other. However, its dependence parameter is not generally equal to the Pearson correlation coefficient between X star and Y star. This is because their Pearson correlation depends on both the copula and the marginal distributions of X and Y. Right. So here that means when we specify the uh, dependence structure between X and Y, that is the dependence structure between X and Y, that is the dependence structure we want in X star and Y star. It is not enough to calculate somehow using the data, the correlation between X and Y, and substitute that into the copula formula. Right? Because parameters appearing in the copula formula, right? As I mentioned, in different copula formulas, there are different parameters. So those different parameters are not necessarily the Pearson correlation coefficient, right? So therefore, we'll have to find out the relationship between the parameter appearing in the copula and whatever the measure that we are going to use as a measure of the dependence between X and Y. So that part I will explain using an example little later. So just to mention that the parameter in the copula, like in the uh, Gaussian copula rho, that is actually the Pearson correlation coefficient, but that is the Pearson correlation coefficient between Z1 and Z2, not between X and Y. So that is again important, right? That is the Pearson correlation coefficient between the two standard normal random variables, not the Pearson correlation between X and Y. right? So therefore, if we want, for example, the Pearson correlation coefficient between x and y to be r, if we say rho equal to r in the Gaussian formula, that will not be correct. Right? So we'll have to somehow find out the relationship between r and rho, and then accordingly, we have to calibrate the value rho and give that calibrated value as the rho to get uh, the required correlation between x star and y star. Therefore, when the particular Pearson correlation coefficient required for x star and y star, we must calibrate the copula parameter, right? So even though Gaussian copula contains Pearson correlation coefficient between Z1 and Z2, in other copulas, they may be completely different parameters rather than Pearson correlation coefficient. So in that case, we have to find a connection between that parameter and whatever the dependence parameter that we are considering for x and y. And then accordingly calibrate that parameter in that copula. Right. So that's a little bit complicated part. I will briefly explain this when we are applying Gaussian copula to generate data. Right. Okay. So now I will look at an example, a general case, explain the procedure to apply Gaussian copula. Right. Here I explain how to use the procedure for a general selected copula. But now let us assume that the selected copula is the Gaussian copula. Right. We know now the expression for the Gaussian copula. Right. So Gaussian copula is given by this expression. Right. So as I mentioned, in order to get this conditional cumulative distribution function of v given u, we have to take the derivative of the copula that we are using with respect to u. So therefore, in this case, we have to get the derivative of this function, this copula. And we can prove that that derivative is equal to this expression here. And we can simplify this by considering the required quantities, which I'm going to omit because it's mathematically a little tedious, but of course we can take some time and do the calculation. And we can show that that expression is equal to this expression. Right. So this is the, well, not that one actually. This is also a part of that. Right. So finally, yeah, this is the expression that we get. Right. So after several steps like this, right, this is where we start. This is the copula. Right. What you need is the derivative of that copula with respect to u, and we want it to get some calculatable expression. And after several steps following like this, I can finally get this expression, which can be calculated when u and v are given, and also rho is given. So this is an important part, right? And then what we do is, once we have that expression, right? So for some other copula, we'll have to get the expression for this thing similarly, but that expression may be much more complicated also. But anyway, we need to get that expression if you want to generate the data, right? So what we do now is the same procedure that I mentioned earlier. Take two random variables, or consider some observations from those where u and w are uniform, u and w independent. So therefore, independently generate a simple u and simple w from uniform 0, 1. And then let w equal to this expression here. W equal to this expression, right? So therefore, w equal to this one. From this expression, I should be able to get an expression for v, right? So v is given by this expression, right? So that is where this the importance of that this function to be invertible, right? So this should be an invertible function so that we can get an expression for v. So in this case, we can get an expression for v like this. It includes u and w. So when we use v to get, when we use u and w to get v using this formula, that v will be correlated with this u here, right? Even though u and w are independent, u and v will be correlated. Although u and w are independent, v is constructed using u here. Therefore, u and v are dependent when rho is not equal to 0. Right? In this case, when rho is equal to 0, they will be independent. And their joint CDF is 0. That is the same as the copula. Both u and v nevertheless have uniform distribution on 0 and 1. Of course, u is uniform, that is what we generated. And v coming from this also will be uniform. Right. Now, once we have u and v, what we do is, in order to get the data from fx and fy, we apply this inverse transformation. Let's say x star is equal to fx inverse u and y star is equal to fy inverse v. And then we get two observations, simple x star and simple y star, say, which are having some dependent structure imposed by this Gaussian copula, right? So depending on what relationship we want between x star and y star, we have to select a suitable value for rho, right? Remember, rho, as I mentioned in this case for a Gaussian copula, is the correlation between Z1 and Z2. It's not the correlation between x star and y star, right? So now, therefore, we have to find out the required rho here so that x star, y star will have correlation, whatever the value that we want. For example, say R, right? So we will decide what value we want for the R using the data, for example. Right. Here I have shown that the marginals coming from that procedure, right? You get x star and y star using this procedure. And we can show that actually fx star coming from like that has the marginal CDF, not the margin, yeah, this is actually the CDF of x star coming from this method is actually the same as the marginal CDF that we want originally, right? And similarly, marginal CDF of y star coming from this procedure is actually the marginal CDF that we want. On the other hand, the joint CDF between x and y, we can get the expression, it is not equal to the actual joint CDF between x and y. Actual joint CDF is fxy. There is no C or G here. G, instead of C, I have written down G here to show that is the Gaussian. This is the conditional, joint conditional distribution generated or prepared through the Gaussian copula. Right? That is not exactly equal to the actual joint CDF of x and y, but anyway, it is a joint CDF. So the resulting variables have exactly the required marginals of x and y, while their dependence is the dependence specified by the Gaussian copula C rho. Right. If x and fy are normal CDFs, then of course the rho will be the same as the correlation coefficient between Z1 and Z2, and then that will be the same as the correlation between x star and y star. But otherwise, as I mentioned, we'll have to do some calibration to get the rho required to be included in the copula, right? So rho is not the correlation between x and y. It is not also the correlation between x star and y star. So if the desired Pearson correlation coefficient between x and y is r, for example, then rho must satisfy uh, this expression here, where correlation between this fx inverse u and fy inverse will contain rho. So that part will be a function of rho, and this r is the required one. So we'll have to solve that equation, including rho, where uv jointly have this copula. So I will now look at a particular example, right? Here I was just mentioning how to generate data with some general fx and fy as marginal CDFs using the normal copula. There I didn't mention what fx I want and what fy I want. Now next I will look at an example particularly specifying what the fx and fy I want, and that will be discussed in the next part of this lecture, because I have already taken more than 1 hour for this part.